Hi, it's Terry Dennery of the MathWorks. So in this video, we're going to talk about feed forward and feedback and why it's pretty important to use both of them actually. Okay, and so let me kind of delete some of the stuff from the last example, spacebar. And essentially what we have here, feedback on electromagnetic torque, which we know is current times the torque constant, compared to our commanded torque. That's really an electrical thing again, because torque and current are scaled essentially, but essentially represent the same thing, right? And quite often you'll hear people talk about, you know, um, designing current loops. And they're talking about feedback control on getting the current that you desire by adjusting voltage, and that's precisely what we're doing. And there's our PID controller that's doing it. You also hear terminology like inner loop, outer loop, and typically the inner loop is that current loop. And because we, in this example, have such precise understanding of the mechanics, we kind of didn't need, you know, the feedback loop on mechanics. But I want to really kind of, you know, assert my opinion that it's always good to have feedback, right? And that the whole premise of feed forward is that you understand your equipment quite well. And so in this example, it's a simple mechanical shaft that's defined, very efficiently by a shaft inertia and a damping constant. And that this interface for our feed forward control, it's precisely the same interface for defining our mechanical shaft even. You can see those same two numbers, right? And if we hit run, we do, superbly. Okay, all right. So what I want to really kind of, you know, um, use as an example to kind of get this point across is, well, what if we don't know? Okay, and so what I'm going to do is define my shaft with 1.5 as a damping constant, which might reflect like a deterioration of a bearing, and let's run that same control. And this time you'll see things do not work quite so well at all. Okay, and so the general idea of feedback is to really kind of deal with the unknown, right? And it could be unknown in what your equipment is, 1.5 for your damping constant as opposed to 1.0. But certainly with that difference, we will see a state, let's call it a change in the operational state as we run the simulation too. And certainly that's, position, velocity, and acceleration, I think, are all kind of expressed by what we're seeing as a difference right there. So again, think of it as our commanded motion as interpreted through this feed forward controller is what we want to happen and what it is combining very nicely to provide a very good estimate what torque should be. Okay, so anyways, but that is not the case right now, and so let's just kind of work on this, right? And so what I want to do is I want to move this over here a little bit so I can get that position command, and I essentially want to create an error. Right? So let's take that commanded position, and let's take our feedback on position right there, right? And essentially we now have an error, and we know PIDs are really good. Oops, it's one of my own. It's not at all what I want. I want the one that ships with Simulink. So there's a PID controller, right? So I'll operate on this error. So let's make a little bit of space for ourselves. Just kind of shift all this stuff over. Let's hit the space bar. Okay. And so now our commanded torque, which really does set our inner loop on our current, is going to have two contributions. One's feed forward and one's feedback. Actually, here's the way I'll do this. This is kind of a good thing to know. Okay, double click on this summation. Well, you make it rectangular and I'm going to put it in two. And you'll see that that's essentially the same thing as an add block, right? And this is just kind of a configuration that I view kind of stylistically being closer to kind of what I want to represent. Anyways, let's kind of set that up like that, and we'll allow it to sum up the two contributions. All right, now, again, I always think it's a good idea, hit run every change you make and just kind of see. what you get. And I'd say that's maybe arguably a little bit better, but it certainly is not good enough. And so just like we did in tuning our current loop, let's tune this mechanical loop, right? And so the values of 1, 1, and 0, which are default to the block, you know, will not work for us. I think you always should hit the tune button even. So let's bring this over here. Okay. And, I ran this one in practice already, and so I'm going to make it even more fast. And I think this works reasonably well. And so these are the new gains right here. Oops, show that. These are the new gains. I think this works. Let's hit the update. Okay. And let's rerun it. Yeah, that definitely looks pretty good. Okay, so a couple things. I want to kind of get into this comment about maintenance and kind of understanding the deterioration of your equipment, because what we're seeing is that if you designed your controls real well, you can't really look at the machine and say it's deteriorating. It's doing what it needs to do. Okay, but maintenance is very much about understanding that the onset of failure is coming. Okay, and that absolutely is revealed in this model, but you're just not going to see it in the command in motion because the controls are working so well. Right. So what I find is pretty useful is, well, let's look at the contributions made by both feed forward and feedback. Okay. And so the feed forward is the yellow and the feedback is the blue. And you can see the feed forward is doing most of it, but there's definitely a non-zero contribution from feedback. All right. And what I'm suggesting is that when you begin to see that become more and more significant, that's your way of knowing. And you can apply all kinds of, very clever, I'll call it numerical analysis. You might even call them AI or kind of deep learning, machine learning type of algorithms that can look at signals like this and draw the proper conclusion. And the conclusion here might be that the bearings beginning to deteriorate. And to just kind of emphasize that point, that if my knowledge is perfect of what the equipment is, which is it's generally operating in a nominal state, um, okay, so my feed forward controller is now matching the actual equipment, you'll see that your feedback will be nearly zero compared to your feed forward component, right? So there's something pretty interesting there, I believe, that will really help you with the many things that you can use these models, especially models that can be very portable, because anything you do in Simulink, you can generate all kinds of code, whether it's C code, PLC code, HDL code, whatever. So um, anyways, main point, feedback and feed forward generally need to work together, and that feedback is great for dealing kind of the the lack of understanding of what the current state of the equipment is, as well as how it's currently operating. So anyways, thank you.